Now let's focus some attention on phosphorus adsorption processes in soils. So what is meant by adsorption with a D? Adsorption is a chemical reaction where phosphorus binds to the surface of soil minerals. These could be aluminum or iron oxides, the edges of one-to-one type clays, and calcium carbonate mineral phases that are found in soils. And the adsorbed phosphorus is oftentimes in equilibrium with the solution phosphorus. What do I mean by this? What I mean by this is that if the solution phosphorus is absorbed by, let's just say, a plant root, then what feeds more phosphorus into the soluble phase? Oftentimes, it's the phosphorus that's adsorbed. That helps keep phosphorus in equilibrium in the soil solution phase. And this adsorption and desorption processes drive diffusion reactions in soils, like you learned in Unit 2 in soil-plant relationships. This is the puzzle that I'm telling you about. So it's important to note that phosphorus adsorption is not cation exchange. Right? We learned about cation exchange via isomorphic substitution and pH-dependent charge in the CEC unit. This is not cation exchange. This is more like, this is an adsorption. This is how adsorption works, right? So I'm going to share with you this diagram. This is the edge on the left-hand side where my mouse is located. This is the outer edge of an aluminum hydroxide or an aluminum oxide mineral. And at the edge, there oftentimes are oxygens with or without hydrogens, right? And here comes orthophosphate in the form of H2PO4. You could probably tell me what the pH is of this if you go back one video. Right? You probably could tell me what the pH of the soil solution is. It's slightly acidic. In any event, the reaction that occurs is this, that H2PO4 reacts with these hydroxides or hydroxyls sticking off the edge of this aluminum oxide or aluminum hydroxide. And what happens is adsorption. So here is H2PO4, right? You see where my mouse is. There's there's two hydrogens, there's a phosphorus, and there's 4 oxygens. Here is H2PO4. It hasn't changed at all, except it's kicked off 2 hydrogens from this one point. Okay? When this reaction occurs, this is adsorption. Oops. Okay, so this is adsorption. Now, I like to describe this in this way in this classroom, that when phosphorus or orthophosphate is adsorbed via adsorption, it's much like when you were a kid and you were maybe at the playground. Maybe some of you went to the playground when you were children or younger. Hopefully maybe you're still going, I don't know. But maybe you played on the monkey bars. And you got on the monkey bars and you kind of went across the monkey bars, right? So adsorption is this on the monkey bars. Adsorption is holding on to the monkey bars with one hand. Now, how easy is it for you to fall off the monkey bars if you're only holding on with one hand? It's pretty easy. And so the bond with adsorption creates a labile phosphorus phase. And what do I mean by that? What do I mean is that the bond is easily broken and phosphorus can fall off the monkey bars, i.e., rather readily back into the soil solution phase. So adsorption feeds phosphorus, as in this case, H2PO4, back into the soil solution phase, which is H2PO4 by itself on the left-hand side of this portion of the equation. Phosphorus loves to be loved. And If you allow this reaction to continue to the right, you'll notice that what phosphorus loves to do is to be held tightly. It loves being loved. I just think of it as it just loves giving minerals a big hug. And this is what this does. This is what orthophosphate does. See the reaction on the far right, or this edge of this aluminum hydroxide. Now look what happened. Look what orthophosphate did. Orthophosphate kicked off uh, kicked off another hydrogen, and it also lost a hydrogen on its own. And I'm guessing there's an oxygen that was moved somewhere as well to form water. And now phosphorus in the form of orthophosphate is given the edge of this aluminum oxide a giant hug. So let's go back to the monkey bar scenario. So initially, phosphorus was holding on with one hand. And I can tell you, it doesn't like that much. It either, well, it really wants to be held on with two hands. And when it's held on with two hands, that phosphorus becomes non-labile. It is really difficult to drop off the monkey bars when you're holding on with two hands. And the same thing can be said for this fraction of phosphorus on the right-hand side of this picture, right? In fact, the right-hand side of this picture corresponds to mineral precipitation. And mineral precipitation ends up with phosphorus being in a non-labile form, meaning it's not readily available for plants to actually see and take up. And oftentimes, the only way for plants to see and take this up is to make a change in soil pH. And even then, this orthophosphate might not let go with two hands or two bonds. Let me tell you something about this, about phosphorus sorption in soils. Every single soil on the face of the planet has some ability to sorb phosphorus, and it's dependent on several factors. It's dependent on, first, clay mineralogy. What types of clays do you have present? 1-to-1 type clays, 2-to-1 type clays, and the pH. And is there any anion exchange capacity present on those broken edges of those clays? Number two, it depends on the amount of aluminum and iron oxides, sometimes we say hydroxides, and the ability for phosphate to exchange with OH groups. This happens at acidic pH values, low pH values, okay? The ability of phosphorus to form associations and be loved by aluminum and iron oxides and manganese oxides. And every soil has a P-sorbing capacity based on the amount of calcium carbonate that's present, or the surfaces that are there. So surface area of calcium carbonate. And what happens is that phosphate can exchange with carbonate on the surfaces of calcium carbonates to form calcium phosphates. And that is phosphate being loved by calcium. With basically a good way to think of it is with two hands. And this occurs at high pH values. This typically occurs above about 7.2, give or take. So, oops, let me go back one. Okay, so I want to stop here with the discussion on P-sorption, specifically with adsorption. Now, hopefully this drives home a point with the monkey bars in one hand and two hands, and how phosphorus just loves to be loved in soils.